Welcome to Data 609, Mathematical Modeling Techniques for Data Analytics for the Master of Science in Data Science curriculum. So the course is really focused on introduction to algorithms and optimization methods for data mining and machine learning. So for all the major data mining and machine learning methods, one of the key component or underlying theory is optimization and algorithms. The reason that we want to take this initiative is that just because, as I mentioned, it's the key underlying theory or formulation is based on optimization methods. But on the other end, what's happening in the field is there are a lot of optimization courses or optimization textbooks, but none of them are specifically focused on data mining and machine learning from practical perspective. I would say that, at least to my best knowledge, I found that this textbook is somewhat unique, that takes the perspective that from practical point of view, how can we model major machine learning algorithms to optimization problem. So the textbook is written by Dr. Xinshe Yang, who is currently at the University of Cambridge. Here for the textbook, you can purchase, and then we can go through it together. As a start, what we want to discuss is an introduction to algorithm and introduction to optimization. So what is an algorithm? Algorithm itself is an iterative procedure. So let's take a look at this example here. For a given problem, for example, an optimization problem, a solution is represented as a vector x. To obtain the correct solution, we usually start with the initial guess, x0. And then you try to update this guess iteratively so that you can get x1, x2, x3, etc., etc. Then the question is, in order to generate a better solution xk plus 1 from an existing solution xk at iteration k, we have using xk plus 1 to update xk, so which is a modification. So question is, do we really want to do that, whether it's a better solution? So now that is a high-level discussion on what is an algorithm. And then for different algorithms, it's really essentially different ways to generate new solutions. Here you have to pay attention to one thing, that is you have to start somewhere. That is to say, the initial guess, x0, which tends to be educated guess. So later, you would realize that for different initial guess, x0, you might come back with somewhat different solutions. So that's why I want to point out the importance of x0. So for finding the square root, for this example, you see, to find the square of a positive number a larger than 0, what we can do is we can use this iterative procedure xk plus 1 equal to 1/2 brackets xk plus a divided by xk. K is going from 0 to 1 to 2, etc., etc. We can start from x0 equal to 1. So for example, if we would say that we, so here we're saying that we want to get the square root, right? So let's suppose that we know that square root of 4 is 2. So let's start with a being 4. So let's say if there is a way that we can get a square root of 4. So starting with x0 equal to 1, let's continue with the algorithm to see that xk plus 1 equal to a half, brackets xk, which was 1, plus a divided by xk, which was 1, so that you get x1 equal to 2.5. If you continue with this procedure, you can see that as a fourth step, we are already very close to the square root of a, which is 2.000000927. This is very close to the true value of square root of 4 equal to 2. So this is one introduction to give you an example on how to find the square root using an iterative algorithm. Yeah, this really just give you a sense on what is the algorithm. Looks still simple, but very quickly we can get into more details of this algorithm. Moving on to slide 4. So as we know that square root of 4 should be could be positive or negative 2 if we really want trying to get that square root. And then we know that we just got one of them, which is positive 2. How can we get the other one, negative 2 then? If you start with the initial solution of x0 being negative 1, by the same calculation, you can see that in x4, we can get the number being negative 2.000000927. So we find the other root by a different initial solution. This is why I mentioned that it's important to start from somewhere, but it's also important to start from some educated guess somewhere that actually makes sense. So now question is where to start. If we choose x0 equal to 0, then the algorithm will simply fail, right? Because we have this xk being the denominator in the second term of the equation. So we cannot have xk being 0 as an initial solution. It cannot be x0 equal to 0. This highlights an issue that the final solution can depend on the initial starting point. In fact, such dependence exists in almost all local search algorithms. So we do need to pay attention to the initial educated guess. As we go along the course, I will give you some tips and key consideration when we come back with the initial educated guess. Now this is an exercise. You can write a short R code to implement this algorithm, which is this square root. I'm going to demonstrate this R code later, but beyond this, there's some other more exercises that I'm going to show. I'm going to use as homework. So just for your own benefit, make sure that you pay attention to some of these exercises. So just give you an introduction on the algorithm. By no means that's all for algorithms, but at least give you a sense that it is an iterative procedure. It have to start somewhere and then with the hope to find the final solution. So what is optimization? A simple optimization problem is to find the maximum or minimum of a real function fx. For example, we know that fx equal to x squared has a minimum value of being 0 at x equals 0. You can see this x star is something special for optimization. X star is the optimum data points of the unknowns. In this case, optimum data point is x star equal to 0 with the value, function value of f min equal to 0 as well. Because the square root of any real number is non-negative. That's why we know the minimum is occurring or happening at x star equal to 0. Here we use x star with a star to highlight the fact that this is a special point, not any point. It's the optimum point, we call it. Okay, this is a formal formulation for the optimization example, trying to minimize fx, which is x squared, and x belongs to all possible values, real values, and which has a global minimum f min happened at x star equal to 0. Notice that this f min essentially is this f min x star essentially is the optimum function value that happened at x star equal to 0, which is the optimum point. So in this case, we can even guess it. But in other cases, how can we come back with an optimum solution? How about any function? In this case, its fx is 3x powered by 4 plus 4x cubed minus 12x squared plus 12. So you can see that the global maximum happened at x star equal to -2. The global minimum, right? So this is a graph on the right-hand side. You can see that this is the shape of this particular function. And the global minimum, the question is whether the global minimum actually happened at x negative equal to -2. Looks like it, right? Because we see some other minimum as well, which is not global minimum. We're going to discuss what is global minimum, what is local minimum, etc., in the coming slides very shortly. But for now, that question is whether this is a global minimum, or you just consider whether x star give you the minimum value. Look like that's the case. But whether there is a way that we can prove that's the case, right? We want to discuss this. And then how about global maximum? Does it happen at positive infinity somewhere or negative infinity somewhere? How do we know that? We know that because we can use some method that's based on gradient approach. So let's say that we take the first order derivative of this function f prime x, which is 12x cubed plus 12x squared minus 24x plus 0, so that we get this gradient of fx, basically the first order derivative of fx. Now we know that if we set f prime x equal to 0, we should be able to find the root of the function. So in this case, we take the f prime x equal to 0. We can set this whole function equal to 0. And then if we take out 12x from as a common factor, then we have x squared plus x minus 2x. So that continue with that factoring, we can come back with 12x times x minus 1 times x plus 2 equal to 0. You can see that for these x prime x equal to 0, it would have three solutions. One of them being x equal to 0, one of them being x equal to plus 1, and the other one is x equal to -2. By going through all the 3 points, we know that f -2 equal to -20 is the minimum. Let's give it a try, right? f0, what do we get? It's positive 12. And f -2, we know it's -20. How about f positive 1? F positive 1, what we got is 3 plus 4 minus 12, that's -5, plus 12. Basically, we come back with a number 7, right? So we have a 7, a 0, a -20, so that at the conclusion, we know f -2 gives us the minimum, which is -20. So we know that since it curves up at this point, as seen on the graph, more specifically, we know that f double prime, second order derivative, comes back with 36x squared plus 24x minus 24, which gives us f second order derivative prime prime -2 equal to put negative back in there, and then we come back with 72. It is larger than 0, so that we know it is a minimum. Right. So for any function, especially for this polynomial functions, in order to get the minimum, what you do is take the first order derivative, set them equal to 0, and find the corresponding roots, and then evaluate the value at each root, and then come back with the minimum or maximum that you're looking for. And then in order to confirm that's the minimum or maximum, you need to take the second order derivative of the first original equation to see if it's indeed larger than 0 or less than 0. If it's larger than 0, then we know we got a minimum. If it's less than 0, we know we got a maximum. So as what I just discussed, right? We need f prime x and f double prime x to determine whether a specific point is a maximum or minimum. However, this doesn't apply to the case when we have the x star is equal to negative or positive infinity. So let's discuss optimality. So we say it's an optimum function, it's a minimization problem, it's optimization. And then what is optimality, right? In general, for simple univariate function fx, where x is a real number, its maximum or minimum occurs at f prime x equal to 0, as we just already discussed. For example, there are 6 maxima and 5 minimum shown in a graph. And then once we set the f prime x equal to 0, we should be able to find the corresponding x values that can give you the maximum or minimum value. Again, for minimum or maximum fx, the critical condition is f prime x star equal to 0 to determine the location for optimality. In other words, I just use the roots that actually gives you the f prime x equal to 0. And then you take the second order derivative f double prime x larger than 0 to find the local minimum, and f double prime x less than 0 to find the local maximum. So here, another example, another exercise that you should do on your own is using R to visualize the univariate function of f prime x is given this form in a domain of -10 and +10, and find all its optimal. So trying to use visualization, use coding visualization to find where that x is. As we know, it's 0, -1, and it's 0, +1, and -2 from previous slide, right? Okay, leave this as an exercise so that you can do it on your own. Okay, before I move on, I do want to show you how we can calculate the how we can do the first exercise. And here is write a short R code to implement this square root algorithm. Hold on, let me. 1 minute. Hold on, I'm trying to get the answer and also zoom to the proper location so that you can take a look. Okay. So here's the answer that we can use to do the the function. So there might be multiple ways to implement that formula depending on the R function you may use. But here is just give you an example. Right? I start with a specific value. You're trying to find the root of a being 4. So as you know, in R you can do a equal to 4, and then start with the initial value x equal to 1, and then you go from there to print each x value. Do this calculation, and then you can print this x value. So the best thing is you can use this example to test in your environment, in your R environment. If you haven't ever used, I'm sure you have used by now, you should at least do a test on this algorithm on your own. Okay, so continue with our discussion on functions with 2 variables. So now that, assume that we have the following function. We have fxy equal to x squared plus y squared. We know it has a global minimum at 0, 0, f minimum equal to 0, because both of the squares of any real numbers x and y are non-negative. But how do we solve it formally, as what we discussed just now, whether we can leverage the same approach as that we just discussed on the 2 variable function. Actually, you can do something very similar, but not quite exactly the same. What you do is you take first partial order derivative in terms of x and in terms of y, and then set them equal to 0. So function partial order derivative of x equal to 2x, and then function partial order derivative of y equal to 2y, set them equal to 0. You can see that the gradient vector of f would be 0. And then you can get the second order derivative as well. Second order derivative in terms of x is, do one more time, it would be 2. And then second order derivative in terms of y would be 2 as well. And then second order derivative for the first order and in terms of x, and then do that again for y, you should be getting second order derivative of x and y, which is really 0 in this case. And then second order derivative in terms of y first and then x, you can get this quantity. So we put them together of those 4 quantities, which is fxx, fyy, fxy, and fyx. Put those 4 quantities together as a form, as a matrix, and then we call it Hessian matrix. Now, this is the definition. Before we go to the definition, let's take a look at this example, previous example that we just took a look. We know that first order derivative in terms of partial order derivative in terms of x and y is 2x and 2y, and then we and then second order derivative in terms of x is 2, and then in terms of y is 2, so that we put those 2 in the diagonals. Those are the 2 that we just got. And then first partial order derivative in terms of x, then do one more time in terms of y, comes back with 0. That would be this quantity. Second order in terms of x, and then in terms of y, right? So that would be 0. How about this quantity? It should be second order derivatives in terms of x, in terms of y first, and then in terms of x. In terms of y first, it's 2y, and then do this with in terms of x one more time, becomes 0. That's why we come back with this 0. I hope this is clear. If not, you should go back again and listen to what I just said. Essentially, the diagonals would be second order derivative in terms of x. The diagonal should be second order derivative in terms of x and in terms of y. But this diagonal is partial order derivative in terms of x and in terms of y, and then this one is in terms of y and in terms of x, second order. And then we see that this Hessian matrix is something we call it positive definite. How do you define a Hessian matrix, whether it's a positive definite? What you do is you get a determinant. The determinant of H is 4 in this case, right? How to get a determinant for a matrix? You know that you use this times this minus those this times that. So which is 4 minus 0, which is 4. We know 4 is a positive number, so we call Hessian matrix itself is positive definite. And then this means F is convex, and the point 0, 0 corresponds to a minimum. In fact, the global minimum. We'll come back with what is convex, what is concave shortly, but for now, you just remember if H is positive definite, then we know it is a minimum. Now, if we extend this algorithm to a more generic function, instead of 2 dimension, suppose it's n-dimensional multivariate function, which is fx, with x1 all the way to xn. Optimum occurs at gradient equals 0, and then the second derivative criterion becomes the definiteness of the Hessian matrix. That is to see, this is a Hessian matrix definition. All the diagonals would be a second order derivative on each individual variable for each of the element. First one is second order derivative in terms of x1, second one would be in terms of x2, third one would be in terms of x3, etc., in terms of xn as well. And then for the off diagonals, what you do is the first one would be second order partial order derivative in terms of x1 and then x2. Next one would be in terms of x1 and then x3, so on and so forth. Right, now you get the idea. Once you construct this Hessian matrix, you want to test whether it's a positive definite. Okay? Any questions on this? Feel free to ask me. Okay, now we have that algorithm or definition. Let's try a more complicated function. fxy is x minus 1 squared plus x2 x squared y squared. Now its stationary conditions are: take the first order derivatives in terms of x set to 0, and the second order and then partial order derivatives in terms of y set to 0, and then from those two equations you can get either y equal to 0 or x equal to 0. And then when substituting y equal to 0 into the first condition, we have x equal to 1. Once y is 0, then we know x would be 1, so that this function would be 0, which is a solution or a stationary point, being x star equal to 1 and y star equal to 0. How about the other condition, x equal to 0? If x equal to 0, then it doesn't satisfy the first condition, because this is x equal to 0 doesn't work. X equal to 0, this is 0, but this one is not quite 0, so it's not going to work. So we know this is one stationary point. But how about we use the Hessian matrix that we just discussed? Instead of doing that, let's do this. Use fxx, fxy, fyx, and fyy. Partial order derivative, second order partial order derivative in terms of x. So on top of this, you do one more round for x. Then this one becomes 2, this one is 0, this is 2y squared, right? So 2 plus 2y squared. And then let's look at this diagonal as well. This really is a typo. This should be y, partial order derivative in terms of y squared. So now, in terms of y, it should be second order would be 2x squared. That's why it's here. How about this one? That should be coming from here, and then do one more time in terms of y. In terms of y, this becomes 0. In terms of y, this becomes 4x. 4xy to be precise, right? So it's now 4xy. And then here, we have to do this one more time in terms of x to put it here. Now this is in terms of x would be 4xy. That's this element. So at the stationary point, we have x star equal to 1 and y star equal to 0, and the Hessian matrix becomes this. It's 2, 2, 0, 0, which is positive definite, which is the same, exactly the same as the previous example. It's just a coincidence. But in this case, therefore, 1, 0 corresponds to a minimum with f minimum equal to 0. So you do the first order first partial order derivative, set them equal to 0, come back with optimum condition, and then use Hessian matrix to confirm whether it's a minimum or maximum. That's a solution method. So here we want to introduce one more concept, that is optimality, strong and weak optimality. A point A is a strong local maximum. You can see here we call it local just because we know if you look at the whole graph, there is some other points that's larger than A. In terms of global, it's not a maximum. But in terms of this local area, it is indeed a local maximum. So that's why we call it local maximum. Where point B within a small flat region, potentially many x stars, is a weak local maximum. Point B could be a region, and then it's a weak local maximum. We call this maximum as well, but both of them are local maximum. Just because this B has a series of potential values, that's why we call this as a weak local maximum. How about point D? It's a maximum among all the possible values. In this case, that's why we call it global maximum. Of course, this point is also a local maximum, and it's a strong local maximum. And point E is a global minimum, just because we know this is a minimum. On the other end, F is a local minimum, C is a local minimum, and also multiple local minimum happen there. And point F is a strong local minimum because it is, as we just discussed in terms of A, it's strong, just one point, it's strong local minimum. This is some definition in terms of optimality. Majority of algorithm, what we are looking for is global maximum or global minimum, but in many cases, we actually could end up with local maximum or local minimum as well. We are trying to either find a global maximum solution, or we have to live with a local maximum solution. Okay, I'll stop here for now and then come back, continue with the rest of the introduction on optimization.